so that you can get the answers, because you cannot able to remember all the answers right now, right? So Atirji, everybody is recording this meeting, or okay, fine. So you can ask questions one by one.
Hello.
Yes, yeah.
Sir, better if you start with the probable questions if prepare. Likewise, we can approach the doubts.
Okay, then I need to think then. Okay, anyways. Okay, fine. So one question may be like in steel making, they basically ask what is segregation. This is a good question. What do you understand by segregation? And can you tell the types of segregations in steels? Hmm. So segregations basically means when we are solidifying the steel, then there is a partitions of these impurity elements or alloying element takes place basically. Hmm. Partitions means alloying element and impurities move preferentially to the liquid phase rather than solid, because you understand, because of difference in solubility limit, right? That means impurities or alloying elements are more soluble in liquid phase compared to solid phase. So when solidification starts, what will happen? Solidification always starts from the boundaries, outer wall, then to inside, right? I think everybody have seen the ingots, right, from your textbook or in the class. So when we are making an ingot, steel ingot for example, then from outer shell the solidification starts and it moves to the center. So when outer shells will solidify, what happens? It will start rejecting the solutes, it will start rejecting the alloying elements or the impurities element to the liquid phase, because inside part is liquid steel but outside part is getting solidified, right? So due to this rejection of the solutes to the liquid, concentration of solute will be more in liquid phase than solid phase, right? Then slowly solidification will increase and finally everything will get solidified. So what will happen? At the center you have more solutes, but in the outer wall you have less solute. Or you can say like this: suppose solidification happens by dendritic growths. So what will happen? Segregation will happen more in interdendritic regions rather than the center part of the dendrite. Fine. So this is the thing. So this is segregation basically. Huh? The segregation is never good for steel, right? So that's why we basically prefer to go for what? Proper mixing during solidification, so that the solute will remain unified in the solid as well as in the liquid. That can be prevented by doing stirring. You can stir the solution while solidifying. That is better. Hmm. So that's why we are using magnetic stirrer. If you have seen in the steel test book, they are written magnetic stirrer. So you are stirring the solution and doing solidification itself. So this is the question, huh? And you might have heard about coring. That is the problem happens in the steels also, coring effect. Hmm. So same. Okay. Anyways, and the question is: suppose you end up with segregation. What can be done? What is the solution? Anybody remember? If suppose segregation has happened already, how you can solve it? So one of the solution is you can go for diffusion annealing or high temperature annealing process. You take the steel to high temperature. What will happen? Obviously, at high temperature, diffusion starts. So the alloying elements which are segregated in certain regions, maybe in interdendritic regions, they start moving and getting distributed everywhere uniformly. That can be done, but it is an expensive process, huh? Because diffusion happens not so rapidly, so it takes more time. So it is expensive. You need to go to a very high temperature, like suppose 1200 degrees centigrade, 1100 degrees centigrade for that. It may take some 12 hours like that. So do you have any idea about inclusions in steels? What is an inclusion in steel, and what is the effect of this inclusion on the steel property? So there is a topic in steel making called inclusion engineering, huh? Because nowadays the steel plants are more concerned about inclusions. Why? Because inclusions means these are basically either carbides, nitrides, maybe oxides, maybe silicates. These are actually compounds, present in the steel. And you can understand the property of carbide, nitrides, oxides, silicates. These are very brittle and hard. But steel is a soft, right? If you compare relatively, steel is soft, but these inclusions are very basically hard. So that means in hard phase is present inside a soft phase. What will happen if you deform it plastically? So what will happen? Cracks will generate where there will be inclusions. So there the cracks will generate fine around the inclusions because they are you cannot deform it. You can deform the steel, but you cannot deform a inclusions because they are hard and brittle. So that is the reason. So we need to modify the inclusions. That is called inclusion engineering. So basically, if inclusion size is bigger, that is a problem. Bigger inclusions are never desirable. And the point you have to remember is we cannot remove 100% inclusions. We can remove excess inclusions, but 100% inclusion involved is impossible. Anyhow, they will come to the steel. Maybe during processing, suppose when we are processing the steel, some erosion of refractory linings may take place. That will contribute to the inclusions, right? Or maybe some oxygen will absorb by the steel during processing and become oxide. It remains as inclusions, right? Sometimes some slags may be carry over in the steels and it will remain up to solidification. So slag is also a silicate or it may be an oxide. So it is an inclusion again. Uh, and during some deoxidation practice, you remember when we are removing the oxygen, we are doing deoxidation of steel. We are adding alloying elements basically like aluminium or maybe your calcium or maybe your silicon. So they become SiO2, L2O3. These are inclusions, no? Oxides, particles. So it is very difficult to remove 100% inclusions, right? So what is the solution? The solution is you can go for inclusion engineering where you are modifying the size, surface, and shape or the structure of the inclusions. Acha, can you tell me? Suppose you have a irregular inclusions and you have a spherical inclusions. Which one will be better for the property, and which one will be detrimental for the
Spherical one.
spherical one? Very good, excellent. Why? Because if the inclusion is spherical, then the stress concentration around the inclusion will be uniform. Fine. But if it is an irregular shape, if it is a needle shape, for example, so where there is a sharp edge, the concentration of stress will be high, but the concentration of stress will be low in other area. So what will happen? A crack will generate where the concentration is high, stress concentration is high. So we have to avoid the stress concentration sites. So that's why we modify the inclusions so that it becomes spherical. The best example is what we are doing. We are adding calcium basically. Calcium, calcium silicide or pure calcium. We are adding calcium particles. Hmm. So that what will happen? It will react with the inclusions and form a spherical particles basically. Hmm. And this once it becomes pure, it can be deformable also sometimes. You can deform this inclusion. There is no issue. Another example of inclusion in steel is manganese sulfide. The problem with manganese sulfide is what? They also get rolled with the steel during rolling operation. Hot rolling I'm talking about. But when it gets solidifies, these inclusions are basically it become hard. Hmm. So a crack may easily propagate through the inclusions because of its hardness. So this is another topic. Okay, fine. You people have heard about secondary steel making process. Can you tell me what are the different secondary steel making processes we do during the processing of steel? Let me see who can answer it. Okay, can you? Okay, they may ask a question like this: what is the difference between primary steel making and secondary steel making? So, what will answer?
So in secondary steel making, basically you are adding scrap percentage or more, like electric arc furnace.
No, no, no. Actually, if you divide the entire steel making, it can be divided as primary steel making and secondary steel making. Primary steel making means we are converting the iron into steel. We are only doing refining process, because you understand, if you talk about pig iron, which is furnace, it contains of impurities, right? It contains carbon, it contains sulfur, silicon, manganese, hmm, phosphorus. So apart from sulfur, all these impurities can be removed during steel making process. So that's why primary steel making process is a refining process. We are converting iron into steel. That is called primary steel making. Can you tell me some examples in by which process we can convert this pig iron into steel? Can you name some processes?
Pig iron to steel, sir, LD converter.
Very good. LD. That process name is basic oxygen process, huh?
Yes, yes.
Or LD steel making, you can say. That is the example of the basic oxygen process. Another example is electric arc furnace. Basically, these two processes are there: electric arc steel making, and then is the basic oxygen process steel making. That is LD process. Hmm. We're doing top blowing. Other processes are also there, like bottom blowing processes, BOP, BOM, those processes. Okay. Anyways, so now what is secondary steel making? Secondary steel making means the customer always wants a particular quality of materials. Huh. But in the primary steel making process, you only make a steel, but you cannot control its quality. The quality control will be done in the secondary steel making process. Secondary steel making process means we are controlling its quality, we are controlling its composition. Right? So what are the things can be done? The first thing is you have to go for degassing. Then sorry, deoxidation you have to do. Then degassing you have to do. You have to do go for desulfurization. Then homogenization, and you have to go for alloying additions, right? You understand my point? So deoxidation means we are removing the dissolved oxygen from the steel. Hmm. Can you tell me how to remove dissolved oxygen from steels? Can you give an example? And can you tell me from where this oxygen is coming into the steel?
Sorry, we are using oxygen lamps.
Yes, yes, good. Actually, when we are converting the iron into steel, we are blowing oxygen into the iron, then pig iron, or your scraps or molten DRIs, right? So the moment we are blowing or lancing oxygen, so what will happen? The impurities will remove, but after impurities will get removed, what will happen? The concentration of oxygen will reach to 1000 ppm, for example, in the steel. And this oxygen is not beneficial during the processing, or the processing, or during casting, or during use, right? So it should be removed from the steel. That is called deoxidation. Removal of dissolved oxygen. Hmm. The easy thing is what you can do. You can you can add some elements which form more stable oxides. Like you can add aluminium, you can add calcium, you can add silicon, right? You can add manganese. The beautiful thing is you have to remember the impurities which are already there in the pig iron, that impurities you can add again in a small amount. For example, you can add carbon, you can add manganese, you can add silicon, right? If you add these things, what will happen? Can you tell me how the oxygen will get removed? Suppose you add silicon into the molten steel, which contain dissolved oxygen. How it will remove?
SiO2.
Yes, because silicon will react with oxygen to form SiO2. So it will take away the dissolved oxygen. It will forming a solid SiO2. Fine. Similarly, aluminium. Aluminium forms more stable oxide. It will form Al2O3, aluminum oxide. So it forms aluminum oxide is a solid. So your dissolved oxygen will trapped in the Al2O3, right? SiO2. Similarly, manganese. If you add manganese, it will form manganese oxide. Okay, fine. Okay, there is a question. Sometimes they ask, what is a killed steel? Can you tell me what is a killed steel? Have you ever heard about this?
Yes, sir.
What is that?
Completely oxygen removed from the steel that is called clean steel.
Killed steel means it's like you are killing the steel. For example, it's not actually killing. It means you are removing all dissolved oxygen from the steel. That can be done by adding aluminium or calcium. You have to remember. Hmm. By adding calcium or aluminum, you can remove the dissolved oxygen from the steel. Most of the dissolved oxygen will be removed because they form more stable oxide, Al2O3 and calcium oxide. But basically, we don't use the best deoxidizer is the calcium. Hmm. Because if you look into the aluminum diagram, L2, L2O3 line and CaO lines are at the bottom of the aluminum diagram. That means they form more stable oxides, calcium and aluminum, right? But we don't use calcium mostly because calcium is highly reactive and it is highly volatile also. Calcium oxide is highly volatile to remove. The recovery will decrease. You cannot recover this calcium oxide again or calcium again, right? But you can add aluminium. Aluminium is just good deoxidizer. Huh? You can add silicon also, right? Okay, fine. Here I can answer one. I have a question. Um, okay, so when you are doing deoxidations, you are adding, for example, you are adding manganese. Huh? The manganese will go into the steel and it will react with oxygen. It will form manganese oxide. Then next step will be what? This manganese oxide is a solid. It will float and it will come to the surface and it will get trapped by the slag present on it, right? In this way, this manganese oxide will be removed. Huh? But the point is, you have to remember the diffusion or the transport of this deoxidation products takes more time, but reaction is very fast. The moment you'll add these into the steel, they will start reacting and form oxides. Fine, aluminum oxide, manganese oxide, silicon oxide, or calcium oxides. But the problem is transportation of this oxide to surface takes more time. It is a slow process. That is a rate determining step, basically. So what can be done? What is the solution to this? There can be two solutions. Huh? The first solution is what? You can purge inert gases from the bottom. Hmm. Right? You can purge inert gases. Which inert gases we purge from the bottom of the steel? Can you tell me any example of inert gases?
Argon.
Hmm?
Argon.
Argon, nitrogen.
Mostly argon and nitrogen. Very good. Argon is preferred. Huh? So if you purge argon or nitrogen, what will happen? It will create circulation in the steel. It will create an agitation in the molten steel, right? So what will happen? That means you are purging the argon or nitrogen from the bottom of the steel vessel. So what will happen? It will help in the rising of these oxides to the surface. In this way, you increase the diffusion or the transport mechanism, right? Another example I can give you. You people have heard about terminal velocity, right? In the mineral processing, maybe in terminal velocity. Terminal velocity means when there are solid particles in a liquid, they start accelerating and finally their velocity become constant. They move at a constant velocity. That is called terminal velocity. So that means you understand you are adding these alloying elements and they're becoming oxides, which are solids, and they try to move to the surface. So they have a terminal velocity, right? But the terminal velocity is very low. So how to increase this terminal velocity? What can be done? You can increase the terminal velocity by purging inert gases. One. And second one is actually this. If you see the terminal velocity formula, it depends upon the d square. D square means diameter square, square of the diameter of the particles. That means if you have big particles, that their terminal velocity is high, right? So what will happen? So all you want that this particle should coalesce with one another and becomes bigger, so that the terminal velocity will be higher. They can reach to the surface at a fast rate. Hmm. So that's why sometimes you add mixed deoxidizers like silicon and manganese together. So it will form silicomanganese, SiO2 dot MnO. They are basically liquid phase. If you see the structure, individual structure of SiO2 and MnO, they are solids. But when they are mixed in form, they are liquid. So SiO2, MnO are liquids. So what will happen? If liquid will be there, they will coalesce with each other easily. They become bigger and they will float to the surface. This is the one of the way. So all I talked about is deoxidation practice. I think you people have understood what is deoxidation and what are the solutions you can do to this. Hmm? Any questions up to this? Okay, fine. Sometimes they ask what is degassing. Degassing is another secondary steel making process. So basically, if you sit for an interview, they are more they ask more questions from the secondary steel making process rather than primary. So what is a degassing? Can you tell me?
Removal of other gases like nitrogen, hydrogen.
Very good. Simple. I already I told you now. The thing is, when you are making steel, at the end of the steel making process, you have dissolved oxygen, right? That is one of the gas, and some nitrogen will be obviously there because you cannot avoid nitrogen. It is 79% in the atmosphere, right? And also some hydrogen comes into the steels because of maybe dissociation of water molecules, or maybe from moisture is getting absorbed, right? So in the steel, in after primary steel making, you have three dissolved gases. One is oxygen, one is nitrogen, one is hydrogen. So you need to remove this hydrogen, nitrogen, and oxygen from the steel, and this is called degassing, removal of dissolved gases, right? Okay, fine. Can you tell me, if oxygen will be there, what is the problem in the processing? Or during solidification, what is the problem? If you have dissolved oxygen, what is the problem during casting or during solidification?
It will create defects.
Yeah, it will create a casting defect. Which kind of casting defects?
Say inclusion.
Inclusions.
Inclusions. Yeah, it may form inclusions, but the problem is, main, it will form blowholes. It will remain as a porosity, big size. Oxygen means it is a gas, na. If it will get trapped during solidification, you have a gas porosity, right? You have a gas porosity, or you have a blowholes. That is called blowholes. If a gas will getting trapped, it will become a blowhole. Can you tell me how to remove the dissolved oxygen from the steel? By reacting this oxygen with carbon, right? Oxygen cannot be removed easily. It will form carbon monoxide by reacting with carbon, right? This carbon monoxide has to remove, right? So if the carbon monoxide is getting trapped in the steel during solidification, it will give rise to what? Blowholes. That is a problem. And the problem somebody told, that is, it may remain an inclusions. It may react with some impurities like aluminium to form aluminum oxide, or silicon to form silicon oxide. So these are inclusions, fine. So inclusions are stress concentration sites. Already I told you about that. What happens if you have nitrogen in the steel during processing, or during rolling or forging, for example, or during deep drawing, for example?
It will affect the mechanical properties of steel,
Yes, yes,
so
very good.
that
It
it
will
will
affect
increase
the
the
mechanical
brittleness.
properties. Basically, what happens? Nitrogen, if nitrogen will be there, nitrogen form nitrites. Nitrates are very hard and brittle. So if they will remain in the steel, then you cannot go for deep drawing process. I think you people have heard about this process, deep drawing. Deep drawing means you can deform the steel to a large extent. You can produce a very thin components, very thin. The diameter will be very less. So you cannot produce a deep drawing component if you have nitrogen, because it reduces the toughness. So nitrogen reduces the toughness, it reduces the deep drawing capacity of the steel, right? and sometimes it can also undergo stress corrosion cracking, right? These are the problems. Hydrogens, if hydrogen will be there, then hydrogen form hydrides, and hydrides are basically unstable. They may dissociate again and become hydrogen, and if hydrogen will be there, then may needs to blistering, or may need to sometimes increase the pressure and leads to crack formations. And if you're doing forcing, this hydrogen will start removing and forming pinholes, but if it cannot remove, it will crack the surface. So hydrogen assisted cracking will be there. Sometimes it may leads to stress corrosion cracking. So these are the problems. So that means you have to remove oxygen, you have to remove nitrogen, you have to remove hydrogen from the steel, right? So that is called degassing. Fine. So degassing can be done by, okay. And can you anybody remember in Seibert's law? Sometimes in interview they ask what is Seibert's law. Sorry, Seibert's law. Recently, who? Amlan Datta. Yeah, Amlan. Sorry, Amlan Mishra. Recently, Amlan Mishra joined JSW, but one day at night he called me and he asked me, "Sir, I have a question. What is Seibert's law? Because they have given me some assignment and this law is there. I cannot understand what is Seibert's law. Can you explain it? Any idea what is Seibert's law? Anybody heard about this in thermodynamics or maybe in extractive metallurgy? So Seibert's law will be applicable in degassing. That's why I'm asking. Yes, somebody have written tell about solubility of gas. Very good. Seibert's law means the solubility of any gas in a liquid, basically in molten liquids, is proportional to partial pressure, root over of its partial pressure. That means if you increase the partial pressure of gas, that means if you increase the partial pressure of oxygen, nitrogen, hydrogen, their solubility in the steel will increase. And just reverse of it, if you decrease the partial pressure, they will come out of the steel. So can you tell me, already I have tell you the answer. Can you tell me how Seibert's law will help you in degassing? So all you have to do is you have to reduce the partial pressure of oxygen, partial pressure of nitrogen, partial pressure of hydrogen. But one point you have to remember, this oxygen, nitrogen, hydrogen all will remain in elemental form, in nascent form, not in molecular form, right? Or like of a gas in a liquid is proportional to partial pressure. Higher is the partial pressure, higher is the activity. Okay, a little more. Two things can be done, right? Either you purge nitrogen or argon into the steel. What will happen if you purge nitrogen and hydrogen into the steel? It will reduce the partial pressure of dissolved gases. How? Because total pressure will depend upon the pressure of these gases as well as the pressure of argon or nitrogen, right? So obviously that means it is diluting, getting diluted. These gases, dissolved gases is getting diluted by argon or nitrogen. So the pressure will decrease. If the pressure will decrease, then it will come out easily. This can be done. And the process is you can have to apply vacuum. That is called vacuum degassing. There are many different vacuum degassing. That means vacuum means you are keeping your molten steel in a vacuum. If you keep the molten steel in a vacuum, what will happen? The atmospheric pressure will go down. If the atmospheric pressure will go down and the pressure of the gases will be higher, so obviously the gases will come out from high pressure region to low pressure region. Fine. I think you people have understood or not. Can you tell me? That means that is called vacuum degassing. You have to apply vacuum so that the partial pressure of these gases will reduce and it will come out of the steel. This is one of the way. So there are many degassing process. Vacuum degassing means you just keep the ladle. Acha, can you tell me what is a ladle at least? What is a ladle? A ladle is a container. You don't know this simple answer. Ladle is a container in which we tap our hot metals or steel. Hmm. It is a container. Suppose you want to take out the iron from the blast furnace, you need a ladle. It is kind of bucket, you can say. It's a container. Similarly, if you want to tap steel, you need a ladle. So you take out the steel in a ladle and put it in a vacuum. So what will happen? Vacuum degassing will happen, right? You can go for stream degassing. You pour molten steel in a stream into a vacuum chamber. It is called stream degassing. And there is a process called VAD, vacuum argon decarbonization. Hmm. That means vacuum argon decarbonization means the name itself is suggesting vacuum argon decarbonization. That means you have to do decarbonization. Decarbonization means removal of carbon from the steel, and vacuum means you have to apply vacuum. And you have to apply argon. Right. So I told you how to remove oxygen. You understood, you have to add carbon, right? Or if already carbon is there, you can remove both carbon and oxygen from the steel. Why? Because carbon will react with oxygen to form carbon monoxide, and carbon monoxide is a gas phase always, right? So suppose you have a reaction, C plus O gives rise to CO, and CO is a gas. And any left side C is solid, oxygen is also in dissolved form, right? It's not considered as a gas. So it will give you CO, gas. So if you apply vacuum, what will happen to, according to Le-Chatelier principle? You, in the right side of the equation, you have a gas phase, and you are applying vacuum. So what will happen to the, according to Le-Chatelier principle? Anybody remember the Le-Chatelier principle? Or Le-Chatelier principle, it tells about in which direction the reaction will shift, right? Yeah, Ankit is saying right. So what happens? See, in your right side you have a gaseous phase. If you apply vacuum, what will happen? The carbon monoxide will easily removed. So if the product is getting removed from the vessel, so that means the reaction will move to the right side. More carbon will react with oxygen, more oxygen will react with carbon. In this way, you can remove carbon and oxygen both, right? And you are applying also argon gas to reducing the partial pressure of carbon monoxide. In this way, you can remove more carbon, more oxygen. That is called vacuum VAD, vacuum argon decarbonization. So in this way, you can remove carbon also. You can remove also oxygen from the steel. And the VOD. VOD is vacuum oxygen decarbonizing. You are applying vacuum, you are applying oxygen, and you are removing carbon also. And there is an important process called recirculation degassing. In the book, you can check RH degasser, DH degasser. The most important is the RH degasser, which is very important. That is called recirculation degassing. You can check, if you have book, you can check. In this process, what will happen? In the ladle, you have a steel containing dissolved oxygen or gases. You have a degasser that is called RH degasser, which have two legs. That is called snorkel, SNORKEL. You insert these legs into the molten steel, and from one end you supply argon. Argon will act as a what? Lifting gas. It will lift the molten steel into this degasser unit, and you are applying vacuum. So what will happen? Dissolved gases will remove. Again, these gases which are free from these dissolved gases, they will into the come into the again into the container in the another leg. So one leg it will enter, and the leg it will come out in this way. That is called recirculation degassing. But the important point about RH degasser is you can do alloying, you can do desulfurization, you can do many things simultaneously in this process. There is a process called vacuum arc degassing. This is very interesting. Vacuum arc degassing. So in vacuum arc degassing, you understood you are applying vacuum, you are doing degassing, and you are providing arc. Arc is always provided to provide temperature, because you don't want to lose heat. You want to give some heat also during the process, right? You don't want your liquid steel will solidify in the ladle. Your liquid steel must be solidified in the cast house, in the caster. Fine, continuous casting, or maybe batch casting, any casting, right? So you have arcing facility also. That is the added advantage. And another interesting point is, suppose the application of vacuum. Suppose you have some inclusions like aluminum nitrides, you have inclusion of silicon dioxide. Hmm. By applying vacuum, you can do what? You can remove these inclusions. How? If you apply vacuum to aluminum nitride, it will simply break into aluminum and nitrogen again, just by application of vacuum. Hmm. Similarly, if you have SiO2, you can and you have carbon in the steel. So what will happen? Silicon SiO2 will react with carbon, from carbon monoxide and silicon, right? Carbon monoxide is a gas phase. Again, it will remove if you are applying vacuum. So the reaction will shift to the right side direction. That means SiO2 will decompose to silicon and carbon monoxide, and carbon monoxide can be removed. So this is another advantage of applying vacuum. And sometimes they ask, what is a Reming steel? Like I told, there is a keel steel, there is a steel called Reming steel. What is a Reming steel? Reming steel means you have to understand what is a Reming reaction first. Reming reaction is nothing but when carbon react with oxygen to form carbon monoxide, that is called a Reming reaction. Carbon is present in the steel, oxygen is present in the steel, or you can apply oxygen into the steel to remove carbon. So it will form carbon monoxide. Carbon monoxide is a gas phase, right? So Reming steel means if this Reming reaction will happen, so the steel will come out as Reming steel. But the point is, you have to remember, we are not removing all the oxygen from the steel. In the keel steel, we are removing all the oxygen, but in Reming steel, we are not removing all the oxygen. So during this removal of carbon monoxide, it will form blowholes. The structure will have lot of blowholes. That is called Reming steel. And Reming steels, you can deform it easily to produce flat components. And during this Reming reaction, also segregation can be avoided. That is advantage. Advantage of Reming steel is, one thing I told, you can produce a very flat component, but from keel steel you cannot produce a very flat component. And second advantage is, due to this Reming reaction, agitation reaction by carbon monoxide during evolution, it will agitate the bath, or it will create circulation in the bath, so that there will be no segregation, right? And it can give you high yield. Okay, can you tell me what is the difference between electric arc furnace and LD furnace or LD reactor? This is a very simple question. What is the difference between or LD process and electric arc furnace process or LD reactor? Can you define?
Sir, in electric arc furnace, we are using electrode,
Very good.
but in LD converter, we are not using electrodes.
Okay, very good. That can be a difference. Nice. Okay, fine. Just remember. Achha, anybody remember by which methods we are producing iron? This may be a simple question in the interview. Name some methods by which we are producing iron. It's a very simple question. Can you answer? Okay, Ankit Panigra is answering something. Yeah, we use scrap in. Yeah, very good, very good. I'm asking, this is a very question. Can you tell me what are the different methods by which we produce iron? At least this is a very simple question. You can answer it. I want an answer from you.
So blast furnace iron making,
Very good. Any other methods?
DRI,
DRI, very good. And the process is called smelting reduction process. Basically, three processes. One is blast furnace iron making, one is DRI or small iron making, and the one is the smelting reduction process. That is called SR, smelting reduction process. blast furnace we get molten pig iron. In DRI or sponge iron making we get a solid iron, sponge iron. And in smelting reduction process also we get a molten metal or hot metal, like pig iron kind of. But it's clean somewhat, more cleaner. So the point is, if you have hot metals, we basically prefer LD process for making steel, like pig iron or from smelting reduction process. But if you are producing DRIs, sponge iron, then we basically prefer electric arc furnace. Or we have scraps, we prefer electric arc furnace. So that is the main difference you have to remember. Huh. LD converter is used, or basic oxygen process will be used if you have molten irons, like pig iron or from iron from SR process. But if you have DRIs, sponge iron, if you have scraps, we basically use electric arc furnace for making steel. Another difference is, in electric arc furnace, you can add any amount of molten metal, you can add any amount of scrap, you can add any amount of DRIs. But in LD process, you cannot add more than 25% of solid irons like DRI, scrap iron, or any, or maybe sponge iron, right? The capacity is only up to 20 to 25%, right? Can you tell me why this is so? Rudra Madhav have answered something that is related to that, and you can add something else. My question is, why basic oxygen furnace or LD furnace don't take more solid or cool materials like DRI, sponge iron, or it's only take 20 to 25%. But electric arc furnace can take any amount of DRIs, any amount of scrap, any amount of sponge iron. Why so?
So because the source of heat in electric furnace electricity, so we can provide electricity to generate heat
Yes,
with
yes,
it,
very
so
good, very
that
good. In electric arc furnace, we are actually providing heat by arcing method. We are producing arc. That is the electric arc. No? You have three electrodes. In between three electrodes, a arc will generate. That is called mm, that is called SE, electric arc furnace. And there is another process called DC, electric arc, where we have one single electrode which is cathode, and your container will be connected to the anode. It will become positive, right? So a arc will produce between your charged material which is positive and your electrode, single electrode, which is negative, right? By generating arc you can generate 4000 degrees centigrade, right? But in LD process, what is the source of heat? Can you tell me?
the
In
coke
LD process, yeah.
coke will be a source.
Sorry.
The coke, sir.
Coke. No, 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 no. We never add any coke into the LD process. Coke will be added into iron making process during blast furnace iron making. Actually, the point is, LD steel making process is a autogeneous process. The heat which is evolved by the oxidation of these impurities like phosphorus, carbon, silicon, manganese, that will provide you heat. You don't have to provide any external heat into the process, right? Do you people understood, or shall I repeat again?
Yes, sir. Understood. The exothermic reactions generate the heat.
Very good, very good. The oxidation process are highly exothermic in nature. We are simply blowing oxygen into the molten iron, right? And it is generating heat by itself because of oxidation of silicon, carbon, phosphorus, manganese. It will release heat. You don't have to give any kind of heat. So that is an advantage, no? The cost will be less because it is because it is a self-sustaining process. So LD process can be a cheaper process if you compare to EAF, right? And emission is also less, but EAF emission is more. Hmm. So these are the differences. And the main difference is, LT process will produce mainly carbon steels, but electric arc furnace you can produce alloy steels. That's why you are using scraps. Scraps means you can produce alloy steel. You can produce stainless steel also. Acha, can you tell me how to produce stainless steel using electric arc furnace? This is a very good question. Huh? What is the composition, basic composition of stainless steel? Can you tell me?
chromium,
Very good. Chromium. Anything else?
The nickel and chromium.
Nickel and chromium. Very good. But what is the percentage of chromium? Minimum percentage of chromium in the stainless steel?
More than 20%.
More than 20%. No, no, no. More than 11.5 or 12.
Yes, sir. Yes.
If the chromium percent will be higher than 11.5 or 12, it can be called as stainless steel because it will never corrode. Basically, never corrode means it will not corrode. It forms a protective layer, chromium oxide layer, Cr2O3 layer on the top. Anyways, so the question is how to produce stainless steel using electric arc furnace. So before moving into that, I can answer you the very interesting point about electric arc furnace is it can produce two type of oxidizing slag. It can produce two type of oxidizing slag. It can produce oxidizing slag and reducing slag, that is called double slag practice, or it can produce oxidizing slag and you can convert that oxidizing slag into reducing slag. You can see this is very interesting, right? In the LD steel making process, which kind of slag is formed only? In LD steel making process, which kind of slag is formed basically? Basic or acidic? What is the basicity of steel making slag? The basicity of steel making, what is basicity? Yeah, this is a very simple question. They can ask, what do you mean by basicity? Basicity of a slag. A slag
The
basicity.
basic oxide divided by acidic oxide.
Very good. It is the weight percentage of all basic oxide divided by weight percentage of all acidic oxide. For example, percentage of CaO divided by percentage of SiO2. It is okay. CaO is basic oxide, SiO2 is acidic oxide. If you have in the slag you have manganese oxide also, sorry, magnesium oxide and P2O5, then what will be the formula? The formula will be what? Percentage of CaO plus 1.4 percentage of MgO divided by percentage of SiO2 plus 0.84 percentage of P2O5. So all basic oxides divided by all acidic oxides. Can you tell me why I have multiplied some values to magnesium oxide and to P2O5? Hmm? The hint is it is related to the strength of the oxide, basic nature and acidic nature. So in between CaO and MgO, which one is strong basic oxide? CaO, right? Similarly, in between P2O5 and SiO2, which one is more acidic? SiO2. So that means P2O5 is a less acidic and MnO is a less basic. So you need to add, multiply some values, right? That's why. This is fine. Anyways, sometimes in industry they call it as a V ratio. You have to remember. They can ask you what is a V ratio in the slag. You need to define like this. I think it is clear up to this.
Yes, sir.
Okay. So what I am discussing now, what was the question? I got diverted. Acha, acha. Different slag practices. So yeah, they may ask you a question, what is the basicity of steel making slag? The basicity of steel making slag is always high, 3 to 4. And basicity of pig iron slag is, or blast furnace slag is only 1 to 1.2. So you can say blast furnace slag is acidic and not exactly acidic, but relatively acidic. But steel making slag is always basic. Can you tell me what is the why this is so? What may be reason we are making the slag more basic in steel making process?
Due to oxidizing atmosphere.
No, no, no. Due to oxidizing atmosphere, no. The point is, in the steel making process, you have to remove lot of impurities. You have to remove silicon. You have to remove phosphorus. You have to remove, yeah, basically silicon, phosphorus, and you have to remove manganese. But manganese don't require high viscosity. Carbon, okay, manganese, okay, fine. So basically, you have to remove phosphorus and silicon. Phosphorus and silicons are what? They are acidic oxides. So if you want to remove them into the slag, you need high basicity, like basic oxides. That's why you are adding more lime into the process to make the slag more basic, so that they will remain in the slag. Their activity will be reduced by this because they form strong bond with acidic oxides. It is okay, or shall I repeat? Is it okay why we maintain high basicity in the steel making slag? Okay, very good. You understood then. Very good. So, yeah. And the interesting point about electric arc furnace is you can make different kind of slags: acidic, basic, acidic, 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 then basic, right? So the point is that this is very interesting. Let me tell you the concept first. The concept is, i- to make stainless steel, you need large amount of scraps, stainless steel scraps, right? You also need some amount of mild steel scraps to add iron, huh? And you also need some amount of nickel. You add high carbon ferrochrome, right? High carbon ferrochrome is source of chromium. Nickel is the source of nickel. Stainless steel scraps will give you both nickel and chromium, and steel some iron. And this mild steel scrap will give you some amount of iron, right? The point is, we can divide the scraps into four categories. First category is what? The scrap which contain lot of volatile matter. They will remove like calcium oxide, zinc oxide, lead oxides, right? The scraps which contains highly oxidizing elements, which will get oxidized easily. For example, aluminium, silicon, they will easily oxidize, right? And there are other scraps which have slightly oxidizing element, like chromium. Chromium becomes Cr2O3 slightly. And there are certain scraps which do not have any kind of oxidizing agent, like nickel, copper. These are the examples, right? So the point is, when okay, fine. The point is, you want to make stainless steel out of these raw materials, huh? You have stainless steel scrap, you have mild steel scrap, you have fresh nickel, and you have added high carbon ferrochrome, right? So what can be done? Acha, can you tell me, stainless steel contains less amount of carbon or high amount of carbon? Let's move to some physical metallurgy, then we'll discuss. You are producing a stainless steel, it should contain high carbon or low carbon? Less carbon. Very good. Why? Otherwise, it will form chromium carbides. Sensitization, right? During welding or during heating, it becomes sensitized. It will become chromium carbides, and chromium carbides will segregate along the grain boundaries. It leads to intergranular corrosion, right? I think you people know about intergranular corrosion, right? I will not discuss that. Anyways, so, but the point is, you may ask a question like, why we are not using low carbon ferrochrome? Why we are using high carbon? Low carbon ferrochrome is three times expensive. That's why. So better to use high carbon ferrochrome, right? So the point is, what will be our first criteria? We have to remove carbon from this molten charge, right? In electric arc furnace, you do melting. You produce a melt containing carbon, iron, chromium, and nickel, right? So now the point is, it is high carbon. How to remove carbon? Can you tell me how to remove carbon? I told you few couple of minutes before how to remove carbon from the steel if you have. In form of carbon monoxide? Yes or no? And carbon monoxide is a gaseous phase. And we know the stability of carbon monoxide. What will increases with increase in temperature or not? Yes. So we will maintain a very high temperature, like 1800 degrees centigrade or more than 1800 degrees centigrade, where carbon will react with oxygen to form carbon monoxide, but the chromium will not react much. It will react a little bit, but not much. So in this way, we can remove lot of carbon from the steel. Now the point is, how to recover chromium. Suppose you want to make 18:8 stainless steel, but since your chromium has gone to slag phase, you want to recover it. So how you can recover it? You can convert this slag into neutral slag or basic slag, right? I told you double slag practice, or I told you you can convert oxidizing slag to reducing slag, right? So you can do what? You simply add some amount of aluminium or silicon into the molten steel, right? What will happen? The silicon and aluminium will react with chromium oxide to form stable oxide, aluminium oxide, and chromium oxide. But chromium oxide will reduce to chromium at high temperature. So all the chromium will recover into the metallic phase. So in this way, you can make a stainless steel by using electric arc furnace. Is it okay? Okay. Sometimes they ask what is the double slag practice in electric arc furnace. Double slag practice means first slag will be oxidizing slag, you need to throw it, and the second slag you will make will be reducing slag. That is called double slag practice. This cannot be done in basic oxygen furnace like LD process. So basically, can you tell me, first question will be why we require this kind of slag practice? It depends upon the impurities. Suppose you want to remove silicon and phosphorus and sulfur. Can you remove sulfur in LD process steel making? Yes or no? You cannot remove sulfur from by using LD furnace. Why? Because the atmosphere is highly oxidizing nature. To remove sulfur, you need a reducing atmosphere, right? Why LD slag is highly oxidizing? Because it contains FeO in it. Lot of FeO. Weight percentage of FeO is high, right? That is why it is oxidizing. But you need a reducing slag. So that's why electric arc furnace is very good. You can make oxidizing slag first to remove silicon and phosphorus, because silicon and phosphorus require oxidizing slag or oxidizing atmosphere, whereas you throw the slag out from the reactor. Then you make a reducing slag. How can reducing slag will be formed? By adding lime and carbon, or you can add some aluminium also, right? So in this way, you can make a reducing slag by adding lime and carbon. It will form calcium carbide, and this calcium carbide can react with FeO to form Fe, lime, and also this lime also react with FeS to form Ca CaO plus FeS. It will form CaS, calcium sulfide, and carbon monoxide. So this is the way, right? So if your steel contain both phosphorus, silicon, and sulfur, you can go for double slag practice. First you remove silicon and phosphorus by doing oxidizing slag. You remove it, then you go for a reducing slag so that sulfur can be removed, which cannot be done in case of LD steel making process. So this is very interesting, right? Electric arc furnace, that's why it is very interesting. Okay, tell me, Acha, can you tell me what is the sequence of impurities removal in this LD steel making process? What is the sequence of impurity removal? Which impurities will remove first, then which impurity, then which, then which? In the first, silicon will get removed. Why? Because silicon form more stable oxide. That's why. Because you are blowing oxygen into the molten iron, right? The silicon will react to form SiO2. It will go to the slag phase, right? And second one is your manganese try to get removed. Then phosphorus, and finally carbon, right? So this is the sequence. First, silicon will get removed because silicon form more stable oxide. Then manganese form more stable oxide. Then phosphorus, then carbon at the end. And okay, can you tell me what is the nature of these oxides? SiO2, MnO, P2O5, CO. Oh, forget about CO because CO remove as a gaseous phase, but SiO2, P2O5, and MnO goes to slag phase. Here MnO is which oxide, acidic or basic? MnO is a metal oxide. Metal oxide means basic oxide. P2O5 and SiO2 are acidic oxides. Okay. So MnO is a basic oxide because it is a metal oxide. You have to remember all metal oxides are basic basically. But silica and P2O5 are basically acidic oxides. Anyways, my point was there they can ask you a question like what is manganese hump and what is phosphorus hump in the LD steel making process. If you draw a plot between percentage impurity removal versus blowing time, then you got a plot where you can see first silicon is getting removed, then you can show manganese curve where manganese is getting removed and again come back into the hot metal that is called manganese hump, and there is a phosphorus hump. Similarly, phosphorus will get removed and again it will come back to the metal that is called phosphorus hump. Hump means they are coming back again into the hot metal from the slag. Right? That is called hump. So the question is why this is happening? Why there is a manganese hump and why there is a phosphorus hump? It is related to the what are the thermodynamic condition required to remove manganese and what is the thermodynamic condition required to remove phosphorus. That is related to that. So can you tell me what are the criteria to remove manganese? What should be the temperature? What should be the oxidizing potential, oxidizing power of the slag? What should be the basicity? To remove manganese, you need low temperature. Fine. You need a basics. You need a acidic slag or a neutral slag, or you need a highly oxidizing atmosphere. These are three things you have to remember: low temperature, acidic slag or neutral slag, or you need a low basicity. Slag basicity would be low. The point is the manganese will become manganese oxide. It will go to the slag phase. That's fine. But the problem is also iron also get oxidized to FeO, right? But the moment you add lime into the process, right? So what will happen? Lime is a strong basic oxide. Manganese oxide is also a basic oxide. So there will be a repel between them. CaO will repel MnO or MnO will repel CaO because they cannot form any bond because they are of same nature. They are all basic oxides. So what will happen? Activity of MnO will increase, and you understand once activity will increase in the slag phase, it will break down into manganese and it will come back into the slag. It will come back into the metal phase again. So this is called manganese hump, and it happens because of increasing in the dissolution of CaO. The amount of CaO is increasing in the slag, or the lime content is increasing in the slag. This happens. But again, this manganese will go back into the slag at the end of the reaction. Why? Because FeO content is increasing. I told to remove manganese, you need high oxidizing power of slag. High oxidizing power of slag means the slag should contain more FeO in it. So this is the situation. And the reaction will be manganese hump reaction will be how MnO plus Fe gives rise to FeO plus Mn. Right? Similarly, phosphorus hump or phosphorus reversal. Phosphorus need low temperature, high slag basicity, and medium oxidizing slag, or optimum oxidizing slag. These are the three conditions required for phosphorus removal. So what happens? Phosphorus is getting removed because low temperature is there initially. Then what happens? Phosphorus will come back because due to increase in the temperature of the bath. Because of oxidation of silicon and manganese, it provides lot of heat. So temperature of the bath will increase. But phosphorus need low temperature. So phosphorus will come back again into the what? Carbon is present now. So phosphorus will reduce by carbon to form P. It will come back again into the metallic phase. But when the concentration of lime will increase, then again phosphorus will go into the slag phase because P2O5 is a acidic oxide and lime is a basic oxide. They form a strong bond between them. So activity of P2O5 or activity coefficient of P2O5 will reduce. It is okay? I think it is clear, or you have any doubts, you can ask me. If you have any doubts up to this. Okay, anybody remember what is jet force number? What is jet force number? We are lancing oxygen into the steel, sorry, into the bath. That is called oxygen lancing. We are doing lancing by using a nozzle. That is a convergent divergent kind of nozzle, or multiple nozzle with multiple holes. Fine. So we have a jet now. We have a supersonic jet. So what is jet force number? JFN. Okay, gas pressure into nozzle dia divided by the height of the divided by the height. Fine, very good. So the point is, now the question will be, if you want to do decarbonization and if you want to do dephosphorylation, then what should be the JFN number? JFN number should be high or low? For what? Can you answer me? They can ask you this question. This is a very important question.
Sir, for decarbonation is faster for more values of jet number.
Yeah, very good. So if JFN number will be higher, then decarbonization will be more preferable, right? If JFN number will be low, then dephosphorylation will be more preferable. That is very interesting, right? Because it depends on temperature, right? Why? Because you understand, if JFN number will be high, that means the height will be less or more. Height will be less,
Less.
and if, because JFN number is inversely proportional to height, if height will be less, JFN number will be high. Decarbonization will be easy. That means the lance height is close to the bath. So what will happen? More penetration. More penetration means more oxidation. More oxidation, more heat. Temperature will be very high, and carbon will form carbon monoxide, and carbon monoxide stability increases with increase in the temperature, right? So obviously carbon will get removed. Decarbonization will be easy. But if the lance height will be less, sorry, more, then temperature will be less, right? So phosphorus removal will be easy. So dephosphorylation will be easy, right? So that's why when we are doing LD steel making, we maintain a high height initially so that the phosphorus will remove. Then later we decrease the height. Acha, they can ask you a question, what is called emulsion formation in the LD furnace. What do you mean by emulsion formation, and what is the benefit of it? Acha, your steel making is over, or I think your steel making classes are over, right? Or in recent semester you are acha, over, right? Very good. So emulsion formation means, suppose you imagine the condition, you have a LD converter, which is a pear shaped furnace, and in that furnace you have molten iron and slag on it, and you are lancing oxygen on it, and with a very high velocity, that is supersonic speed. So the moment the supersonic oxygen jet will strike the bath, what will happen? It will create a crater, hole kind of thing, crater, right? That then further what happens? Periphery of the crater will throw the, or it will throw the metal and slag to the top, right? It is splashing will be there, and when the splashing will be there, the lot of carbon monoxide will try to remove, and in this way it will form a foam, and this foam later converted into what? Emulsion. Foam means a gas will be trapped in a liquid, that gives rise to foam. Two things are there: carbon monoxide is a gas, and slag or metal is a liquid, right? That is a foam. But the emulsion means this foam will convert into emulsion. Emulsion is, these are droplets actually. Droplet of what? Droplet of gas, metal, and slag, right? And due to formation of these tiny droplets of gas, slag, and metal, the surface area will increase to a large extent, right? Due to large surface area, the reaction rate will be high. So in this way, the impurities removal will be fast. That's why in LD converter, impurity is removed within 20 minutes. That is very advantage of the LD process because of this emulsion formation, right? I think it is clear or not? Is it okay? I have a question. What is the difference between top blowing and bottom blowing process in steel making process?
In top blowing, we are blowing oxygen from the top of the furnace, and in bottom blowing, we are blowing oxygen from the bottom of the furnace.
Okay, very good, very good. So actually we can have top blowing process, basic oxygen process, bottom blowing basic oxygen process. We can have mixed blowing or hybrid blowing, right? In the top blowing process, we are blowing oxygen from the top itself. And there is a process where we are blowing top oxygen from the top, and from the bottom we are blowing inert gases like argon or nitrogen. And there is a process called bottom blowing process only, where we are blowing oxygen from the bottom itself, and we are doing nothing else, right? But with oxygen we are also purging some hydrocarbons. Can you tell me why we are purging hydrocarbons with oxygen from the bottom? What is the advantage of purging these hydrocarbons? It will protect the lens, or it will protect the nozzle. How? Because when we are blowing oxygen from the bottom, due to oxidation reaction, lot of heat will release that may melt, or that may destroy, or that may erode the nozzle part. So if you provide hydrocarbons, this hydrocarbon will protect this nozzle. How? Because hydrocarbon will break down, it will undergo cracking, it will decompose, and this decomposition of hydrocarbon is a endothermic process. It will consume heat. So that in this way you can increase the lifespan of the nozzle. You understood my point? But from when we are doing top blowing, we are doing water cooling always. We are protecting our nozzle by doing water cooling. So that is called water cooled lens. Hmm. That's why the lens tip is made up of copper, because copper has high thermal conductivity. It can lose heat easily, and it is a water cooled copper, right? Anyways, uh, what do you think? Bottom blowing is more advantageous, or top blowing is more advantageous? Which one is more advantageous, bottom blowing or top blowing process?
Top.
No, bottom blowing process is more advantageous, huh? Because if you do bottom blowing, you can reach equilibrium easily. You can work near to the equilibrium conditions. But if you do top blowing, you are working far away from the equilibrium conditions. The point is what? The circulation will be better if you are doing bottom blowing. The circulation or agitation will be better because you are blowing from one side of the furnace. You are not blowing at the center of the furnace. You are blowing one side. If you are blowing from one side, what will happen? Circulation will be there. So better circulation means faster removal of impurities. The oxygen distribution will be uniform everywhere because you're blowing oxygen. You want to send oxygen to every part, so it will be faster, right? But when you're doing top blowing, the top part will get agitated more, but the bottom part of the reactor will be not agitated more. So there will be always a difference in oxygen. There will be always difference in the impurities level. So that's why bottom blowing is more advantageous. So that means if you talk about yield is higher in bottom blowing because the amount of oxygen will be less in the molten steel. But in case of LD process, top blowing, the amount of oxygen will be high. Dissolved oxygen will be high. Can you tell me if dissolved oxygen will be high in the steel, what is the problem? Then you will lose lot of iron in form of FeO. Once Fe become FeO, it will join slag phase, so you will lose lot of iron. So in LD process, you lose lot of iron in this way. because of non-uniform distribution of oxygen, due to a non-uniform stirring, and due to more dissolved oxygen. But in bottom oxygen flowing, stirring is good, well distribution of oxygen, removal of impurities will be fast and easy. That is the thing. Do you know what is slag carryover? This is a very simple question. What is slag carryover? Actually, what happens when you are tapping the hot steel using a ladle, sometimes some slags will also go into the steel. That is called slag carryover. You don't want your slag to carry. You want only steel, molten steel to trap. This may happens during basically in electric arc furnace. In electric arc furnace, we have a eccentric bottom tapping process where we tap our molten steel from the bottom. So what happens? Sometimes the slag may carry over. Slag also go into the ladle, right? So that creates a problem, right? That is called slag carryover. Achha, sometimes they ask what is productivity? What is productivity in case of iron making? Can you justify? Productivity is called Q by P. You have to remember, huh? Productivity is called Q by P. Q is the coke throughput divided by coke rate. Coke throughput means kg of coke per day you are using divided by how much kg of coke you are using for 1 ton of hot metal. Right? That is P is equal to Q by K. You have to remember. Or you can say how much ton of hot metal you are generating per meter cube per meter cube per day. Or you can say how much ton of hot metal you are producing per day per meter cube of the furnace. So productivity actually depends upon coke rate, fuel rate. It depends upon your area of the hearth of the furnace. It also depends upon the working volume. Anybody remember what is working volume in the blast furnace? Or what is working height? That is better. What is inner height, working height?
Working heights at 22 meter,
Sorry?
22 to 24.
No. I'm not asking any data. I'm asking the height. From which part of the furnace to which part of the furnace?
Start to bose,
Hmm?
start to clear.
Stack to 2 year. Yeah, it is called working height. Very good. Working height means in that height most of the reaction is going on. Right? From the stack means from the throat. Not stack is a big reason. Na? From the throat or from the stoke line to the 2 year reason is called working height. And that volume is called working volume. Very good. And what is inner height then? Inner height is from stoke line or throat to tap hole. And total height is the bottom of the furnace to the top of the furnace. Huh? You have to remember this. Acha, important question. What are the different practices by which you can increase the productivity or you can reduce the coke consumption in the blast furnace? Can you tell me? This is the most important question. What are the practice you can do in the furnace so that you can reduce the coke consumption and you can increase the productivity? Nobody remembers. You can tell me one point at least. Do you know the cost of the pig iron depends upon coke? 50%, 45 to 50% cost of the pig iron depends upon the coke. You can imagine. Coke is very expensive because of the processing, because of the raw material availability, and because of the import also. We are importing metallurgical coal from the what, Australia mostly. Because we don't have much reserve. So that's why we have to reduce the coke. Coke rate means what? What is coke rate? Coke rate means for to produce 1 ton of hot metal, or how much amount kg of coke is required. That is called coke rate. So we have to reduce it. And productivity, I told you this one. How much ton of hot metal we are producing per meter cube per day, or per day per meter cube. So what are the practices you can do to increase the productivity and decrease the coke rate? This is a very important question. I think you might have get a question during your end semester on this. Somebody have written pulverized coal. Very good, very good. So to increase the productivity of the blast furnace and to decrease the coke consumption, you can do lot of injections in the 2-year region, right? Through 2 years, you can do lot of injections. The first is you can inject oil. Oil is a hydrocarbon, right? You can inject oils. Oils are hydrocarbons. The moment you inject oils, it is a hydrocarbons. What will happen? It will react with coke carbon to form what? It will decompose to form what? Carbon monoxide and hydrogen gas, right? So what is the advantage? You are getting carbon monoxide as well as hydrogen also. Can you tell me which one is a better reducing agent, hydrogen or carbon monoxide?
Carbon monoxide.
No, hydrogen is a better reducing agent. Hydrogen is 5 to 6 times better reducing agent than carbon monoxide. You have to remember, because of its small size, lightweight, and lot of things, and its utilization. Volume percentage eta H2O. If you check percentage, hydrogen utilization is very high at high temperature. If you go to a very high temperature like 900 degrees centigrade, 1000 degrees centigrade, it utilization goes to very high level. But if you check the carbon monoxide utilization, it is low at high temperature like 900,000 degrees centigrade. And if you check the utilization at 821 degrees centigrade, both utilization amount is same. The percentage utilization of carbon monoxide, percentage utilization of hydrogen is same at 821 degrees centigrade. But if you increase the temperature to 900,000, more than 1000, then utilization is reducing in case of carbon monoxide, but hydrogen is increasing. So in this way you get advantage. More hydrogen you generate, more reduction will happen. And another advantage of using hydrogen is what? The product is H2O. There will be no pollution, no greenhouse gas. Because greenhouse gas means what? Carbon monoxide and carbon dioxide. But you are not generating any carbon monoxide, carbon dioxide if more hydrogen will be there. Because the product is H2O, water molecules only. It is okay. You people understood my point? The first point is you can inject oils. But the problem with oil injection is oil price is high. And the problem with oil is it is an endothermic process. It consumes some heat. The raft will go down. Anybody remember raft, RAFT in the blast furnace? Raceway adiabatic flame temperature. You have to maintain raft inside the furnace, which is present in the 2-year region. Raft should be maintained. Raft should not be go high or should not go less. If raft will increase, the problem will be what? Your hot metal contain more silicon. That is the problem, right? You don't want more silicon in the hot metal. Okay. But if your raft will go down, your hot metal will having more sulfur content. And other problems will be there. Maybe some freezing might take place in the top of the furnace. The slag or hot metal may freeze inside if the RAPT will be decreased. So RAPT will be always maintained. It should not go up or it should not go down. So if you are purging oil, it will undergo what? Endothermic process. So RAPT will go down. That is the limitation. But the advantage is you are getting hydrogen and carbon monoxide both. Similarly, you can decrease the coke consumption in this way. One of the way you can purge uh, natural gases by reforming it, or by like that also. Natural gas, if you purge, what will happen? Methane, CH4 react with carbon to give you again carbon monoxide and hydrogen. So this is another advantage. You are again generating hydrogen. Similarly, if you inject PCI, pulverized coal injection, you make the coal fines, you screen it and pass it through the, you dry it and pass it through the tuyeres in a auxiliary tuyer into the furnace. So what will happen? This will burn and release lot of heat as well as lot of carbon monoxide. In this way you can, but this PCI you have to remember, these are non-metallurgical coal. This third way. Fourth way, you can inject steam into the process. Steam. You convert the water into steam and you inject it through the tuyeres. If you inject steam, what will be the product? Can you tell me? When the steam will react, that means H2O will react with carbon to give you what? Again, carbon monoxide and hydrogen. This is very interesting. So that means all this process is generating hydrogen gas, and hydrogen is a better reducing agent than carbon monoxide. So obviously the productivity will increase, the co-consumption will go down. But all this have a limitation, that is these are all endothermic process. They will consume some heat also. I think you people have understood up to this. Yes or no? Okay, fine. And the thing, you can increase the hot blast temperature. The hot blast temperature you can increase to a large extent. You can go to 1200 degrees centigrade, right? So that means you are inputting some amount of heat already. So less amount of heat will be required inside the furnace. Already we are putting some heat. So burden on the coke will be less. Acha, can you remember what is the function of coke inside the blast furnace? Can you tell me? What are the main function of coke in the blast furnace? Just tell me three important function.
Sir, coke support modern material.
Very good. That is the one of the most important property. Anything else? It acts as a fuel. No? It will burn and release heat energy. You need heat energy for smelting, right? And it acts as a reducing agent. It will directly react with iron ore to give you iron, or it may react. It may react with carbon to form carbon monoxide, right? So coke will be used as a fuel. Coke will be used as a reductant, and coke will hold the burden materials. It will sustain the burden, right? So these are the important points. Okay. They can ask you a question. Why we cannot reduce the coke to a large extent inside the furnace? Suppose earlier coke rate was 450. Now it has been reduced to 230 to 240 with addition of PCI, like 220 kg of PCI or 250 kg of PCI. But you cannot reduce the coke further below 240 or 230. Why? Why you cannot reduce? It lies, the answer lies, which I told you few minutes before. Actually, coke is the only material which will remain in solid, right? It will either burn or it will remain as solid. It will not melt. But in the furnace, you are having melts. The liquid iron is there, liquid slag is there. So coke is the solid. So there is a zone called cohesive zone. If you check the blast furnace structure, you can check there is a cohesive zone which formed in the just above the tuya region, in the basically in the lowest stack and in the Bosch region. Cohesive zone contains solid cokes, but everything is liquid. That means you have molten slag and molten metal. So if you have solids, then only the hot carbon monoxide gas will go up through this solid coke because it will provide a permeability. Similarly, the hot metal and slag can penetrate through this solid coke. But if everything will be liquid, then nothing can penetrate. So there will be no reaction. The furnace will not work. Right? So that is the main advantage of using coke. That means a limited amount of coke should be given so that it will remain as solid. It will not become fines. And coke is very strong. No? Coke is very hard and strong. It will not break. and reactivity of coke is very high. Calorific value of coke is very high, and coke is free from moistures, volatile metals, and ash content is also very less. So these are the properties of coke, right? Okay, any questions from your side, from blast furnace iron making at least? Okay, fine. Can you tell me what is the need of alternative iron making? If you have blast furnace iron making is excellent because blast furnace is a very excellent countercurrent reactor. It has high thermal efficiency, high chemical efficiency, it has high productivity, its availability is also high, 95% to 98%. Everything is good in blast furnace. But what is the problem with blast furnace? We need a alternative route of iron making. Obviously the blast furnace have some limitations. That's only we are going into alternative route now. So can you tell me what are the limitation of blast furnace? Already I told you the answers just before. Blast furnace need a transient raw materials, right? Transient raw material means without coke blast furnace cannot run, and I told you the cost of the pig iron depends upon the coke. 50% cost is taken by the coke itself. So you can reduce the cost. Why will lie upon the coke? That is the problem. You understood? By reducing the coke, you can reduce even the cost, right? So that is the one of the driving force. A second driving force is pollution is very high because of coke. You are making coke in a coke oven furnace. Coke oven furnace produce lot of greenhouse gases, right? So we have to reduce the pollution also, right? And the manufacturing cost is also high. Anyways, these are the things. And the thing is, blast furnace always need pellets and sinters to run. You cannot run a blast furnace with fines. You cannot run a blast furnace with low quality raw materials like waste containing iron or anything like that. You need sinters and pellets, which are very stronger, harder, and with a proper size, right? So you need to make sinters. You make to make pellets. Though that will add cost to the process. You can avoid sintering. You can avoid pellets. That can be done if you are using alternative route of iron making. You understood my points? Is it okay up to this? Okay, so anybody remember SLRN process? What is SLRN process or what is rotary kiln iron making process? It comes under which process? It comes under DRI iron making or sponge iron.
DRI.
Okay, very good. And there we are using coal or natural gas? We are using coal,
Cool,
right?
sir.
We are using coal. So you can imagine that means we have practically avoided the use of coke, right? So this is a very simple example. That's why alternative route of iron making has come, right? Sponge iron making, because we are not using coke here. We are using non-metallurgical coal. Non-metallurgical coal is plentifully available, right? Acha, what is the limitation of sponge iron making? Can you tell me? One of the limitation of sponge iron making is what? The capacity of furnace is low. The furnace capacity is very low if you compare to the blast furnace. Lot of energy is lost in the gas phase. Like 40% energy, input energies get lost. You have to remember. And we get a very porous product, which are highly reactive. So it may get reoxidized. Huh. This is the problem. One is the loss of energy. One is the porous products. Highly porous product is sponge iron is highly porous, highly reactive. And second one is we are getting a solid product. We need to melt it again. Huh. And your slag is already present in that. That is the other problem. Huh. And these are the problems, right, basically. But advantage is more advantage. Huh? More advantage means we are avoiding use of coke. We are avoiding use of basically coke. That is the main advantage. Similarly, can you tell me what is Corex process? Corex process comes under which kind of process? Pig iron making process, or blast furnace process, or DRI process, or SR process? Corex.
Yes, sir. Yes, sir.
Yes, SR, smelting reduction process. So Corex process is very interesting. Corex process contains two reactors, different reactors. Blast furnace have one single reactor, DRI plants have one single reactor, but Corex process have two reactors. The top reactor is called reduction furnace, where we generate sponge iron or DRIs, and bottom reactor is the smelter gasifier, or that is the melting furnace. Hmm. The interesting point about this is in blast furnace we have same thing. In the top part is the DRA part and bottom part is the liquid part. But here it is completely different. It is completely separate one. We have two separate furnaces, right? So what happens? The hot reducing gases which are coming from the melter gasifier will be interacted with the reduction furnace, right? So the iron will become sponge iron. Then by using screw conveyors, you can feed the sponge iron into the melt gasifier, a melter gasifier or the melting furnace. And in the melting furnace, you charge oxygen, you charge flux, you charge the any other raw materials if you want. Hmm. Right? This process will go on, and you can use the waste gases in other processes because it contain more carbon monoxide, basically, to run a turbines, for example. And also, it produces pure iron, really. And there is a process called rotary hearth furnace. This is very interesting. Rotary hearth furnace means there is a rotating hearth inside the furnace which will rotate, which will take the material from one location to another location. But there is different amount of heat is there, right? Here in blast furnace, what happens? The material is moving from top to bottom. But in rotary furnace, the hearth is rotating. It is rotating the raw materials from one place to another. The raw material is not moving, right? So in this way, you can use fines. That is the advantage of it. Because in blast furnace, you need permeability. But in this rotary hearth furnace, you cannot need permeability, you can use fines. But the problem, limitation of rotary hearth furnace is the metallization is very low, 80% metallization, hardly. Right. That is the limitations. Otherwise, it is good. It produces nuggets, basically. It produces nuggets form of metals. Okay, ask for an make. If you have, you can ask. Okay, but remember, what are the different internal structures in the blast furnace? When a blast furnace is working in working condition, what are the internal structures generates? From top to bottom, can you tell me? The top internal structure generate is called granular zone, granular, because everything is solid there. That is actually stack reason. The upper stack is called granular zone, where everything is solids. Only indirect reduction takes place there. The ore, iron ore is in solids, the coke will be in solids, right? Then just below that, there is a cohesive zone. I already told you about cohesive zone. Cohesive zone is a what? Some liquid will be there, some solids will be there. Solids are coke, and liquids are molten iron and molten slags, or fusion zone, right? Next come active coke zone, right? In active coke zone, the coke will undergo burning and release lot of heat and carbon monoxide. Then below that, two-year or combustion zone, because from the two-year, hot blast is coming and reacting with carbon to form carbon monoxide, and lot of heat is generating, right? So that is a combustion zone. Then below that, there is a dead man zone. Sometimes they ask what is a dead man zone in the blast furnace. Dead man zone is a zone which contains solid coke. These cokes didn't take part in combustion process, so that's why they remain solid, and they remain in solid and they are floating on the hearth, right? That is a dead man zone. Entire burden is sustained on it, you can say. And below that, there is a hearth zone. And importance of hearth zone is the slag metal reaction takes place at the interface. the container of the liquid slag and liquid metal. Right? Can you tell me what is thermal reserve zone in a blast furnace? What is a thermal reserve zone in a blast furnace? Can you tell me? Thermal reserve zone means that is a isothermal zone. Isothermal zone means the temperature is constant, right? That means we have two things in the blast furnace. One is the gases, hot gases, and we have a solid ore and coke. So when the temperature of the coke and when the temperature of the solid and temperature of the gas will remain same, there will be no heat transfer between the gas and solids. That is called thermal zone, right? So in thermal zone, the temperature of the solids, that means temperature of the coke and iron ore, will be equal to the temperature of the hot reducing gases. That's called thermal zone. If you go above thermal zone and below thermal zone, it will be different, right? Like near the 2-year zone, the temperature of the hot gases will be more, but temperature of the solid will be less. So there is a heat transfer from the gases to the solids, right? Okay, what is the difference between direct reduction and indirect reduction? Can you tell me?
Direct reduction are using on carbon, and indirect reduction you are using CO, carbon monoxide.
Very good. So direct reduction and indirect difference is direct reduction means directly the solid coke is reacting with iron ore to give iron. But whereas in indirect reduction, the carbon monoxide, after converting from coke, it is reacting with iron ore to give iron. Right? So, Acha, can you tell me any other difference between direct and indirect reduction? Which one is endothermic? Which one is exothermic? Indirect reductions are always exothermic and direct reductions are always endothermic in nature, right? So that's why indirect reduction always occurs in the stack portion, in the upper stack region, because temperature is low and they release heat. But direct reduction always occurs in the Bosch region or the lowest stack portion, right? Okay, next question is what is the difference between pelletization and sintering?
In sintering, we are using 100 plus mesh screen size, and in pelletization, we are using minus 100 mesh screen size.
Okay, the difference between sintering and pelletization, the similar. What is the similarity? Both are agglomeration process. We are converting fine into agglomerates, bigger size particles, right? So in sintering, if you see the charged metals, we are charging what? We are charging somewhat bigger size particles. We are charging coke breeze. We are charging some flux. We are charging some silica, like that. Uh, It undergo granulation process, then it will go for sintering. But in uh, pelletization, we are charging fine particles, very fine iron ore or ultra fine iron ore, right? Then we are adding some bentonites, which is act as a binder. We may add some flux or not. Basically, we do not add flux, and we add some moisture, water content. So moisture content is very important in this pelletization process. So these are the difference in the raw material, right? So in sintering we have coke, but in we are charging coke, but we are not charging coke in pelletization process. We are adding a binder in pelletization, which is bentonite basically, or some organic binder we may use. But in case of sintering, we are not using any kind of binders, right? And other difference are sintering is carried out using Dwight Lloyd sintering machine, but pelletization is carried out by using what drum pelletizer, disc pelletizer to produce what green pellets. Then this green pellets will undergo induration in using what a moving crate as well as a rotary kiln, right? So there is a difference, obviously. Can you tell me which one is more expensive, sintering process or pelletization process?
Pelletize.
Pelletization process is very expensive because you need very fines, right? You need more grinding. More grinding means more energy you need to spend. And also you are using two different. You need rotary kiln as well as moving grate, right? Okay, which one is more stronger, pellets or sinter? Pellets are very strong. You have to remember the strength of pellets are very high. High. That's why it can be transported from one location to another location without any problem. But if you transport sinters, they will break. They will generate fines, right? Any other difference? What is the limitation of pellets? The pellets limitation is pellet sticks with one another. These are balls. Now they will stick with one another. That's the problem during processing. If you add flux, there will be more sticking will be there. That is another problem, right? You cannot make fluxed pellets, that's why. But you can make fluxed sinter easily. And other problem is pellets also undergo swelling, right? During heating, it undergoes swelling, and due to swelling, they may lose its strength, lose its porosity. Right? So that is the end problem. But there is no problem of in case of sintering, right? These are the things. And advantage of pelletization is pellets is what? Pellets are spherical balls, uniform size, so they will give you more voids or more permeability in the blast furnace, right? But sinter will not give that amount of because sinters are irregular shape, irregular size. I think it is clear up to this. Any other questions you have?
सर ये जो बैलेंस चार्जिंग वाला था मैं सर वो
Sorry,
वाला थोड़ा
wait. Just wait. Yeah, now you can tell me. Huh?
तो बैलेंस चार्जिंग ऐसा कुछ था
Pellet charging.
बैलेंस
Acha, bellless charging. Okay, fine. Bellless charging. So bellless charging is a new technology where we are not using any kind of bell on the top of the furnace. In the bell charging, we have two bells or three bells or four bells. The lowest one is the bigger bell, then other one is will be a smaller, and above one will be a smaller, right? But the problem with bell charging is what? It will undergo M profile or V profile basically, and it will undergo segregations. So the reducing gases cannot penetrate uniformly throughout the materials. So there will be a improper reduction happens. So productivity will go down. But if you use a bellless stop, what will happen? The bellless stop have a rotating chute. This rotating chute will uniformly distribute the raw material inside furnace because it rotates in 360-degree. It will uniformly distribute the raw material. That distribution of raw materials will be uniform. There will be no formation of M profile or B profile kind of thing, basically. Okay, but if you use a bell top, then there will be M profile, B profile kind of thing, right? I think it is clear, or any questions you have?
yes sir
You can look the pictures in my notes, which is there in the website. Huh? Beautiful pictures are there. You can understood by looking at the pictures how rotating chute works. Okay. Any other questions you have? You can open. You can ask without any hesitation. Huh? Acha, I cannot see the Vedant. Where is Vedant?
So some are traveling home. That's why
Okay, fine.
some are traveling. So
Mhm.
that's
Okay, any questions from your side related to steel or iron?
सर हाइट ऑफ प्रेशर वाला हाइट ऑफ प्रेशर
Acha, what is height of pressure? Very good. This is very interesting. Height of pressure means from the top we are applying a pressure on the outgoing gases. See, blast furnace is a counter current reactor. Counter current reactor means from the top solids are moving downwards and from the bottom hot gases are moving upwards. So this is the opposite direction movement. That's why it is called counter current reactor, right? So this hot gases contains what? Carbon monoxide. The carbon monoxide has to reduce the iron ore. But the problem is what? Because of high velocity of the hot blast, this carbon monoxide is moving at a very high velocity towards the top, and they leave the furnace without much reacting with the iron ore because the residence time is very less. So that is called carbon monoxide utilization. Percentage carbon monoxide utilization. There is a formula. percentage CO2 by percentage CO plus percentage CO2. That is called percentage carbon monoxide utilization, right? So you understood, because of high velocity of the hot blast, the carbon monoxide is moving very fast to the top of the furnace, and it remains unutilized because it cannot find more time to react with the iron ore. So you are losing a lot of carbon in form of carbon monoxide. That's why the reaction is also called solution loss sometimes. You are losing carbon in form of solutions. That is called solution loss reaction. So if you give a pressure from the top, so what you can do? You can increase the residence time of the carbon monoxide gas. The carbon monoxide gas stay for more time at the stack region. And it can take part in the indirect reduction. Okay, so your productivity will increase, your coke rate will decrease. That is the advantage. Also, if you apply more pressure from the top, you can increase the blast volume through the hot blast by, if you increase the more volume of hot blast, you can increase the productivity. More oxygen will be available in the furnace. In this way, you can increase the driving rate, you can say. Is it clear, or you have any issue? I think everybody have understood. It is okay. And in this way also, we can decrease the silicon content. That is very interesting. How silicon content can be decreased by increasing the high top pressure. See, I told you a reaction. SiO2 will react with two carbon, will give you silicon plus what? Carbon monoxide. Yes or no? SiO2 plus two carbon will give you silicon plus carbon monoxide. Yes or no?
Yes, sir.
So in the right side, see, in the left side you have what? Solids. SiO2 is a solid, carbon is a solid. But in the right side you have what? One silicon is a solid and carbon monoxide is a gas phase. So if you apply pressure from the top, that means you are increasing the pressure. So reaction will be shifting to the left or right now? Hmm?
Again, sir,
Oh,
again.
okay, I need an answer from Ankit. Ankit, you can answer it, I think. Om Prakash? Okay, the question was SiO2 solid react with two carbon solid will give you Si silicon solid plus carbon monoxide gas phase. You are increasing the pressure. So the reaction will shift to the right side or left side. In the earlier discussion, I told if you have a product in the right side, if you apply vacuum, then you can shift the reaction to the right side. More carbon monoxide will form, right? Very good. Atrija is saying left side. Very good, very good. Obviously, that means if you apply a vacuum, then you are removing carbon monoxide. You are removing silicon kind of thing, you can say. Silicon, you are not removing silicon, that means you are removing carbon in one way, you can say. But if you increase the pressure, just opposite, what you are doing, you are moving the reaction to the left. That means SiO2 will remain as SiO2, and SiO2 means it will remain in slag phase. It will not come into the metal phase because it is not becoming silicon, right? So in this way, you can reduce the silicon content by applying high top pressure. So these are the three advantages. One advantage, you can increase the productivity and you can reduce the coke consumption. How? By increasing the residence time of carbon monoxide in the stack portion. You are doing more indirect reduction. Second point is, you can blow more air or more oxygen into the furnace. The driving rate should be high. More air, more oxygen means more reactions, more carbon monoxide, right? And third one is, you are reducing the silicon content because you are not allowing this SiO2 decompose to Si. These are the three advantages. Is it okay? And okay, very good. There may be a questions why we do steam injection and oxygen enrichment simultaneous. What is the benefit of doing steam injection through the 2 years and oxygen enrichment through the 2 years simultaneously? What is the advantage of it? The thing is, I told you, when you are injecting steam, the steam means H2O. It will react with carbon to generate CO and H2. That is very good because we are generating more hydrogen, and hydrogen is a better reducing agent than carbon, I told you. But the problem with this process is it is an endothermic process. It will consume heat. So raft will go down. But I told you have to keep the raft same. You do not have to increase the raft or decrease the raft, right? So if you enrich the blast with high oxygen, what will happen? More combustion will be there. More oxygen available means more combustion will be there. So more heat will release. So the loss of heat by the humidification of blast or loss of heat by the steam injection will be controlled by the heat evolved during this combustion by by moving more amount of oxygen into the furnace. So that's why the endothermic reaction will be controlled by the exothermic reaction. The react will be balanced. Is it okay? Similarly, can you tell me why PCI injection, fuel injection, and any hydrocarbon injection is done with oxygen enrichment? Can you tell me? Answer is same. I told you na, if you inject oil, if you inject PCI, if you inject any hydrocarbons, they will undergo decomposition. So it is highly endothermic. But if you inject oxygen, it will exothermic. So they will be balanced. The raft will be balanced. But the important point you have to remember, you cannot generate carbon monoxide above 900 degrees centigrade because, sorry, below 900 degrees centigrade. If the temperature will be below 900 degrees centigrade, you cannot generate carbon monoxide because stability decreases. Na? The carbon monoxide stability decreases with decrease in temperature, but increases with increase in temperature, right? So that's why direct reduction is very important inside the blast furnace. Because of direct reduction, you are generating carbon monoxide. For example, FeO plus C gives rise to Fe plus CO. You are generating carbon monoxide by direct reduction. So it is benefit. You are generating carbon monoxide by two ways. One is due to combustion and another one is due to this direct reduction. So that will help in the indirect reduction, right? But you cannot generate carbon monoxide below 900 degrees centigrade. That means in the upper stack, you cannot generate carbon monoxide. You can have a carbon deposition reaction, but you cannot have a solution loss reaction. Okay, any other questions you have? Can you tell me if hydrogen is a very better reducing agent, 5 to 6 times better, why we are not using hydrogen till now? What may be the problem? The answer is very simple, no? The hydrogen is either hydrogen is produced by electrolysis of water or it can be produced from the non-renewable resources. So we do not have such capacity to produce such amount of hydrogen by electrolyzing the water, right? Capacity is very less. We cannot produce, and the production cost is also very high. So hydrogen production cost is very high. The electrolyzer do not have such capacity to produce that amount of hydrogen, right? And other things is if you produce hydrogen from non-renewable resources, fossil fuels, it creates an again problem, pollution problem, right? So these are the problems actually.